All right, we're going to look at the universal law of gravitation and how that translates into universal gravitational potential energy. So how much potential energy do I have at very large distances, not just near the surface of the Earth, where we've been using mgh. Okay, so what happens as we go away is that force of gravity is no longer constant, and so we need to go ahead and use the conservative force is equal to the negative derivative of a potential energy function with respect to x, and we're going to use that relationship to go from the universal law of gravitation to a potential energy function. Now, we are going to write the universal law of gravitation just a little bit different here with a negative sign and a unit vector denoting the r hat direction. So what this looks like is because r is always measured away from the center of our object, the force of gravity is always pulling the other object in, so they're going to be opposites. So we do have to have a negative sign in there just to say that it's an attractive force. Okay? So our next step is we want to grab a potential energy function. So we're going to take this and we're going to say, okay, the potential energy function is going to be the negative integral of our force function dx. And so we are going to choose this to be our x direction. And so we'll choose this point here as x equals 0. And you can imagine that it will go off to infinity. We are not going to have negative values because radius, if I just move it to the other side, I just kind of switch my direction as positive x direction. All right. We do need a reference, though. Where should our potential energy be 0 at? And it works out that we're going to choose our reference to be infinity. And at infinity, the gravitational potential energy is 0, much the same as when we used mgh here on maybe the surface of the Earth. I might call the ground a height of 0, and so there's 0 potential energy there. This is going to lead us into kind of a funny situation to talk about energy, but hopefully we'll get through that. So what we're going to do is we're going to go ahead and take the integral from infinity to some position r. Okay? All right, so here we go. So the potential energy of negative, the integral from infinity to r of this function, negative big G, big M, little m over x squared, because we are in the x direction here, so dx. So I'm just going to make this x and I hat then. All right. Take this integral and we get a potential energy function for gravitational potential energy, let's be specific there, of negative, so you thought you had enough negatives, but another negative comes out, so we get 3 of them here. Big G, the mass of one of the objects, the mass of the other one divided by r. Okay? And so our potential energy is a negative number. Masses are positive, r is always a positive number, and so we get a negative potential energy. Now, if I look at a graph, what that looks like is I have this point when I'm at the surface of the Earth, and I have this negative amount of potential energy. And the further I get away from Earth, my potential energy gets bigger and bigger and bigger until I reach infinity when my potential energy is 0. And if you go inside a sphere, your potential energy also drops off to 0. And the nice thing about this is our graph has, values that are finite. Okay? So we have a 0, we have a finite value here, and then as we go off to infinity, it just approaches 0. Okay? So this is what our gravitational potential energy looks like. I'm going to go ahead and I'm going to show you how do we find escape velocity using this gravitational potential energy function. I'm also going to go ahead and show you another way we can do energy conservation with it as well. I'm going to link those 2 videos down in the description.